the Lewis structures and the Vesper theory actually explained a lot, all right? Lewis structures, Vesper theory, they predicted a great many things. In fact, let's just remind ourselves of some of the things that we learned from Lewis symbols and Lewis structures. We talked about the combining power with hydrogen, remember that idea? Back in Mendeleev's day, where nitrogen will have a combining power of 3 when you mix it with hydrogen. Oxygen has a combining power of 2. Carbon has a combining power of 4. And that's nicely explained by the Lewis symbols, because the unpaired electrons, those are the ones that are available to form covalent bonds, right? Unpaired electrons available to form covalent bonds. And so for carbon, for example, we would then show it either as a cross, but you know that a cross is really a tetrahedron. And all 4 of these bonds, as I've been saying over and over again now in this most recent unit, these are all equal, right? All 4 bonds are equal. And that's not just what the model says, that's what you actually measure. Okay, but now when you go back to what we studied in chapter 3 with quantum theory, it doesn't quite all make sense. Because in quantum theory, we talked a lot about atomic orbitals, right? You have 1s2, 2s2, 2p2 for carbon. Remember all that stuff? Well, it's all coming back now, okay? So we would describe them in orbital diagrams. Those 6 electrons, when you talk about the valence electrons, those are the ones that we've been focusing on. Those are the ones involved in all this bonding. Well, they have different energy levels. They come from orbitals of different energy levels. 2 of those electrons are at 2s sublevel, and 2 of those electrons are in 1 each of the redundant p orbitals at the 2 level. So how do we get from those unequal, slightly unequal electrons to something where all 4 of the bonds are exactly equal? You see, the Vesper theory alone and Lewis structures alone don't quite answer all of that we can now measure. And then, of course, with all the quantum theory that didn't exist at the time that, Gilbert Lewis made all this modeling. So we needed a new model that explained all that kind of bridged the gap. And that new model is called valence bond theory. And this came from Linus Pauling. This is the same Linus Pauling that gave us the electronegativity idea back in the previous chapter. So this was now in the late 1920s. Right, so this is once quantum theory has made its presence, and now we're trying to use that to better understand, to build a better model that explains more of the experimental data. And we're going to spend a lot of time talking about this valence bond theory, and I'll just warn you now, it gets a little existential. Okay, I'm going to be drawing some nice pictures for you that you might not be able to draw yourself. I'll try to go slowly so that this will make some more sense. But let's just start by describing some of the things that we have with valence bond theory that's new. Okay, and what's new, the first thing that's going to happen is that we're going to use the s and the p orbitals, and we're going to combine them. They're going to hybridize. And they're going to do that. When they hybridize, they're going to be equal energy. So they're going to hybridize into equal energy, what we're going to call hybrid orbitals. And so, for example, here's a picture I would have drawn for you back in chapter 3. Let's say we're at n equals 2. We're looking at the n equals 2 electrons and the sublevels. And we have the s sublevel at n equals 2. That's going to be the the orange sphere. And then within that orange sphere, we have the p sublevels, right? And then we have 3 degenerate orbitals. One is on this plane, right? There's one on this axis here. And then there's the third one. Okay. And what we're going to do now is take the electrons that are in those orbitals, and when it forms covalent bonds, I should stop and say, this is still an accurate model for how carbon would be arranged all by itself if it wasn't interacting with anything else. In fact, let's put the electrons in there, because we'll have 2 electrons in the 2s, and then we'll have 1 in one of the p's and 1 in the other p's, and then that's it, right? That's it. It has 4 valence electrons. And if carbon was unhybridized, let's just say this is carbon by itself. What the new model is going to do is, when it's bonded with something else, and in this case, let's say it's bonding with methane, so it's going to form 4 equal bonds. Well, when it does that, it's going to turn these into 4 equal hybrid orbitals. Oh my goodness, I'm so zoomed in that my stylus is too fat to read. 4 equal hybrid orbitals. And those can be drawn along the axes of a tetrahedron. They would in fact be kind of tetrahedral. For the same reason that when we first talked about an SN4, how Vesper theory tells us the repulsion would orient those 4 pairs of electrons. It would be along a tetrahedron. Well, now we're going to have 4 hybrid orbitals, so they will also be organized around the axes of a tetrahedron. And I don't need to outline them. You can see all 4 of them drawn here. But now we'll have 1 of those 4 electrons in each of them, because now they're equal energy. Okay. Now, when we do this, we're basically taking, we have, how many orbitals total are there here? There's 4 total orbitals. But they're not exactly the same. One is s, and then we have 3, 1, 2, 3 p orbitals. So if we merge them all together to form 4 equal hybrid orbitals, we describe that with this nomenclature, sp3. There's 4 things total. There's 1 s and there's 3 p's. So these would be called 4 sp3 hybrid orbitals. Now that's what you would get if carbon is going to form 4 bonds. When it forms 4 bonds, it would have an S and a 4, like in this molecule up here in methane. This has an S and a 4, right? So with this new model, that S and a 4 is going to be 4 hybrid sp3 orbitals. And we'll go over this in much more detail. I'm just introducing you this idea for you, okay? Now, carbon can do all sorts of different kinds of bonding. It doesn't always form 4 bonds, but it can form up to 4 bonds. But we'll be looking at some molecules where carbon is only going to be bonded to 3 atoms. Sometimes carbon's only bonded to 2 atoms, okay? But in each case, you have these 4 orbitals to work with. In this new valence bond theory for covalent bonds, it's a different model to explain covalent bonding. We can take a look at all those 4 and describe what the hybrid orbitals would be depending on what kind of molecule carbon is in. So when carbon is SN4, like in methane, we will then have the 4 sp3 hybrid orbitals. We'll look at some examples where carbon will be an SN of 3. And in that case, we're only going to merge 2 of those p orbitals with the s orbital. We would have this situation. We're going to merge 1s with 2 of the p's with the 1s. That will give us 3 equal energy sp2 hybrid orbitals. And that's going to leave one of those p orbitals unhybridized. Right? And you'll see that when you have carbon in a molecule where the steric number around carbon is SN3. We'll look at some examples where carbon is involved in bonding where it's only an SN of 2 in that molecule. This model then would predict that when carbon is SN2, that hybrid orbital situation is going to be where it just takes one of the p orbitals to hybridize with the s orbital. That will give you then 2 sp hybrid orbitals, and it's going to then leave 2 of the p orbitals unhybridized. Now, I know that sounds really complicated, but this is just an introduction. We're going to be going over lots of examples of these. The second new thing that you get with these, with the valence bond theory model, is that now we're going to describe different kinds of covalent bonds. And one of them, we're going to define something that's called a sigma bond. And that will use the Greek symbol sigma. This will describe single bonds. And we're going to also describe something called pi bonds, using the Greek symbol pi. And we'll see what can form a single bond and what can form pi bonds, sigma bonds and pi bonds. Pi bonds, these are going to be what's involved with double bonds and triple bonds. And you'll see that this will come about by having bonding between these unhybridized p orbitals. Right. These are going to be involved in double and triple bonds. The single bonds, those are going to be much more simple to describe. In fact, let me start by describing the simplest kind of sigma bond that you can make. If we just take 2 hydrogens and build our molecule H2, molecular hydrogen, right? Each hydrogen has 1 electron, and that electron is in an s orbital, right? So there's 1 s orbital and there's the other s orbital. And if we bring those 2 together to form a shared bond, like this, I might show that the overlap of each one is kind of like this. I've shown you this before, but now we can describe the density of where that shared electrons really are found. And I draw it all over the molecule. But with this idea, we can really define an area right in here where we have an overlap of the shared electron density. And this overlap, that's really going to define what the sigma bond is here. That's the easiest one to describe, but I think this will be a little bit clearer to you if I start going through a couple of examples. Now that you have just the term here, let's just start with one easy example, and we'll use methane. We'll stick with methane as our example, and we're going to talk about sp3 hybridization. So this is where the steric number is 4. When you have a steric number of 4 around the central atom, that will be exhibiting the sp3 hybridization. In our example here for methane, they're all going to be in shared pairs. Now, the actual electron distribution that we might describe of these hybrid orbitals, that still comes from quantum mechanics. And it's actually, and you can read this in the textbook, it goes into this a little bit. It actually has a major lobe of electron density and a minor lobe. But for simplicity, we're just going to talk about the major lobe and describe them in the four orientations of the tetrahedron. And in fact, for simplicity, for clarity, it's usually elongated out because it's a lot easier to draw these pictures when they're elongated like this. Okay, so I already showed you above here what would happen when we go from carbon by itself. Let's just focus on the carbon. And when it's all alone, we might describe the orbitals, again, looking like this, but we can also describe them using our orbital diagrams and our electron configurations, right? We did that before. The electron configuration is 1s2, 2s2, 2p2. And if we were to draw that in an orbital diagram, but now we'll have the increased energy going up, right? So this is carbon atom. This is what I mean by itself. It's not bonding with anything. But now we're going to describe what happens to the valence electrons in carbon when it's bonded to four things, when it takes on an SN of 4. According to the theory, then, these four different orbitals, 3 p orbitals and 1 s orbital, will all hybridize into 4 sp3 orbitals, right? These are now 4 equal energy sp3 hybrid orbitals. And notice on this energy diagram, it's above the 2s and below the 2p. It really is, in an energetic point of view as well, hybrid between the 1s and the 3 2p's. Right? And each one of them has 1 electron. And we can place each one of those electrons into one of these 4 lobes. And let's just do that. 1, 2, 3, 4. These are the 4 sp3 hybrid orbitals. And just like in the tetrahedron, you can even look at the bond angle between them that they'll be forming. Right? This is all going to model what we've already looked at in VSEPR theory. We're just using a different modeling scheme to describe the bonds that are formed. Here are the 4 hydrogens that are involved in methane. I already showed you what one of them looks like. So these are the 4 hydrogen atoms. Each one has its own electron in a 1s orbital. Okay? And the 1s orbitals, they are going to merge with one of these sp3 hybrid orbitals to form the bond. And here's what one of them looks like. Here's one of the atoms, one of the hydrogen atoms, and it's sharing its 1 electron with the 1 electron that's in one of those 4 sp3 hybrid orbitals. Right? And you can see the same thing in all of these. I won't draw the 4th one back there because it gets messy. So we still have the same idea. It's a shared electron pair. It's a covalent bond. But now we're describing this with these new terms, sigma bonds. Remember, the sigma bond is this area of shared electron density between the two. So we would call this a sigma bond. There's another one here. There's another one here. All single bonds are sigma bonds in this model. And in this case, we're forming a sigma bond by merging an s orbital with 1 sp3 hybrid orbital. Right? That's what's shown here. We're making a sigma bond by joining an s orbital from the hydrogen atom with one of the 4 sp3 hybrid orbitals from carbon. Up above, when I showed this for hydrogen, molecular hydrogen, we also made a sigma bond by joining 2 s orbitals. So that's another way to make a sigma bond. We took an s orbital plus another s orbital. That's also a sigma bond. This is what we found with H2. And as you'll see with the next couple of examples, you can also form sigma bonds if we have any two hybrid orbitals overlapping. So we could have, for example, one sp3 hybrid orbital plus one sp3 hybrid orbital. Or it could be one sp2. We haven't talked about sp2 yet. I just introduced them to you. And one sp3. Or we can have an sp and an sp, any combination. Any combo of hybrid orbitals. And it's specifically the overlap of the electron densities. That's what forms the sigma bond. And before I leave that subject, let me just make one more statement about the sigma bonds and where this overlap is. Notice in methane here, we've got the carbon nucleus is here. Let's put carbon back in there. And the hydrogen nucleus, let's change color. The hydrogen nucleus is over here. And the shared density of the shared electrons is along the axis between the nuclei. That's going to be important with this model building, right? The overlap is along the bond axis, right? That's the line that connects the bonded nuclei. I'm simply describing what this model describes, basically. All right, the sigma bond, the overlap of electron densities will always be along the bond axis. And you'll see later on why that's important to distinguish. You feel overwhelmed yet? It's okay, take a deep breath. We're going nice and slow. Let me emphasize this with a couple more examples, okay? Let's just stay with sp3 hybridization. All right, so that means that we still have an SN of 4. And one of the nice things about a complicated subject like this is if we have enough time, we go over enough examples that you'll start seeing these complicated ideas over and over and over again. It's going to start to sink in. Okay, so anytime you have a steric number of 4 on your central atom, it will show sp3 hybridization with this model. So let's look at the example here. What do we got here? We got ammonia, NH3. We've looked at that plenty. So let's look at it now in the context of this model. If we look at nitrogen alone, unhybridized nitrogen, this is what we have. The 2 electrons at the 2s level, and then we have 1 electron each in the 3 degenerate p orbitals. Now, let's take a look. Let's write what nitrogen looks like over here, the Lewis structure, just to convince you that it has an SN of 4. And there it is. There's 4 pairs of electrons. 3 are in bonding pairs and 1's in a lone pair. But now those 4 packets are going to be defined by these hybrid orbitals. We're still going to have sp3 hybridization because it's SN of 4. Now, take a look at what's present in those sp3 hybrid orbitals. Right, now, let's see, how should I show this? Well, let's just look at the diagram right here. Now, one of them has a lone pair. And the other 3 have an unpaired electron, and just as before, the unpaired electrons, those are available for bonding. Just as we've been talking about all along. Now, here's what it looks like in the model. You've got your three, it's drawn right down here below. Here's your three hydrogens, individual, and each one has an electron in the 1s orbital. And now you've got nitrogen that's undergoing sp3 hybridization, so it still has the 4 sp3 hybrid orbitals, and 3 of them are bonding with the hydrogen, sharing its electron. Remember, those 3 had, I guess I should really draw them in different colors. Whoops, that's the same color. All right. But then the other 2 electrons from nitrogen, that's in a lone pair. But that lone pair is now over there in the last sp3 hybrid orbital. There's still 4 sp3 hybrid orbitals, but now only 3 of them are involved in making sigma bonds. And again, these are sigma bonds. The shared density of shared electrons is along the bond axis. And there's 3 of them now. So this lone pair, that's over here. I like being neat. All right, let's take a look at water, our friend water. You know what the Lewis structure of water looks like by now. I don't think I need to tell you. But let's look at the oxygen in water. Here's the Lewis structure. It also has an SN of 4, right? 1, 2, 3, 4. When it's unhybridized oxygen, when it's not bonded to anything, we can still describe the electron configuration and orbital diagram for those electrons in isolated oxygen all by itself. 2 in the 2s orbitals, and then we have now 4 in the p sublevel orbitals, but we've got 2 of them are in a lone pair, and then we have 2 that are unpaired, and those are available for bonding. Now, when this hybridizes to form the 4 sp3 hybrid orbitals, now we have 2 lone pairs because we've merged. We have 2 lone pairs and we have 2 unpaired. And you can see that in the model here as well. It's still SN4, so it's still 4 sp3 hybrids, but now 2 of those hybrid orbitals hold the lone pairs, and the other 2 are involved in forming sigma bonds with the 2 hydrogens. And once again, these are all describing sigma bonds. We haven't gotten to pi bonds yet. So this was all with SN4. If you take a look at any of these molecules, it has an SN of 4, right? Methane had an SN of 4. I didn't draw the Lewis structure here, but if I did, you would see there are the steric number. There's 4 packets of electron pairs surrounding that central atom. So that's an SN of 4. With ammonia, we've got 1, 2, 3, 4, except here one of the packets is a lone pair. With water, we have SN of 4 as well. These are all SN of 4. And with that, you have 4 hybrid orbitals, which we're calling sp3. And there's no unhybridized p orbitals. So let's look at something other than SN4. Let's look at SN3. So now for any molecule that has an atom in it that's that has an SN of 2, that will undergo sp2 hybridization. Now with sp2 hybridization, we have 3 equal hybrid orbitals now. And we call them sp2. Right? There's 3 of them. There's 1s, and there's 2 p's. Let's take a look at that in a slightly different way, the way we did before. Once again, if we look at unhybridized carbon in the ground state, we know what that looks like from quantum theory. I don't need to go over that again. But now, what happens to those valence electrons when carbon finds itself bonded to only 3 things and not 4 things? Now, in this case, it's going to reorganize those 3 things into the 3 hybrid orbitals. These are sp2 hybrid orbitals. There's only 3 of them. Here they are. But they're equal energy. There's 1 atomic orbital left over. That's this 1 p orbital. There's 1 unhybridized p orbital. So here, these are the atomic orbitals. Let's put it this way. And these are the hybrid orbitals. Overall, we started with 4, so we need to end up with 4. But when it's sp2 hybridized, that leaves 1 of those p orbitals unhybridized. All right, and that's this guy out here. Now, what does that look like from a model's point of view? So here, actually, let me write this down. We have 3 equal hybrid sp2 orbitals, and then we'll have 1 unhybridized p orbital that's left over. And for the example on this one, we'll look at formaldehyde. The Lewis structure for formaldehyde looks like this. That's the common name. When you go on and take organic chemistry, you'll learn a more formal naming system for molecules. This will be called methanal. That's just for your information, for all of you going on to organic chemistry someday. For this class, you just need to know what the structure is in this case, or at least understand how to interpret the structure. That's probably a better way to put it. All right, so you should be able to derive that Lewis structure on your own. And once you've done so, creating the correct Lewis structure, now take a look at the steric number, for example. What's the steric number on this carbon? How many packets of negative charge are surrounding that central carbon? We've got 1 here, we've got a second one here, and then this is a double bond. You don't count them 1 as each, it's a double bond. You have 2 bonds there, but it's taking up 1 position. All right, as far as Vesper theory goes, all right, so this is Sn of 3, and that organization would be trigonal planar. That's what we learned when we studied Vesper theory. But if you only have 3 packets of negative charge, they will distribute themselves in a plane. And we went over all that. Now, in this case, the bond angles might not be exactly the same because one of them is a double bond and 2 of them are single bonds. We went over that as well. Since we're on this subject, take a look at the oxygen. What's the steric number on that oxygen?
3.
It's also 3. Very good. You've got 1 lone pair, 2 lone pairs, and you've got the double bond. So we have an Sn of 3 on both of these. So the Sn of 3, what's trigonal planar? What's trigonal planar are going to be these 3 equal energy sp2 hybrid orbitals. Now, how might I draw that out? Now, this is where we use our artistic license. You can try to draw these if you want. These are also all drawn in the textbook, okay? But I'll try to go a little slow here. And now, of course, I draw these all the time, so I've had a lot of practice on this. Let's just draw the carbon. So here's the carbon. Let's first just describe the organization of those trigonal planar, those 3 hybrid orbitals. All right, these are going to be the 3 sp2 hybrid orbitals. So let's label these. Okay, they're of equal energy and they're approximately, the same amount apart from each other, but they're all in a plane. These all define a plane. How might I draw that plane? Let's see. Kind of like that. It's trigonal planar. Now, what's bonded? Actually, before I do that, let me show the unhybridized p orbital, because we need to describe 4 overall. Remember, now when it's sp2 hybridized, we're going to have the unhybridized p orbital. That will be perpendicular to, the orientation will be perpendicular to this plane. Now remember what a p orbital looks like. I need to remind you of that. A p orbital is this bilobe shape. We have one in the, call it the x orientation, one in the y orientation, and one in the z orientation. There's 3, remember, but each one is bilobe. That's just the theoretical distribution of where those electrons in that one orbital could be found at any given time. So when it's unhybridized p orbital, it's bilobe. So I'm going to draw one lobe above the plane and one lobe below the plane. Okay, this is our unhybridized p orbital, and there's only one. And that's showing with the lobes above and below the trigonal plane. But remember that those 2 lobes, they define the distribution of any one of those 2 electrons that can be found in that atomic orbital. This is an atomic orbital. Let's put the electrons in. Now I'm just following what we have shown in the diagram here, okay? We're going to put 1 electron in each of these regions. So we'll put 1 in each of the 3 sp2 hybrids, and we'll put 1, here, let's put it down here, in the unhybridized p orbital. All right, now take a look at the Lewis structure. We've got 2 hydrogens bonded here. And I showed you what that looked like earlier when we had hydrogens bonding to other atoms when we're using this new theory. Remember, the hydrogens, that just has 1 electron here in an s orbital, but the s orbital is overlapping with the hybrid orbital. In the earlier examples, it was an sp3, but it's just a hybrid orbital. And that overlap of shared electron density gives us the sigma bond. So we're going to have the same thing here with these 2 bonded hydrogens. And let's just draw them in. Here, I'll put them in red. So here's 1 hydrogen, and it's going to share its electron. And here's another hydrogen that it's going to share its electron, but let me put the s orbital that it's in. Okay, and this area of shared electron density, that's going to give you the sigma bond. Okay, and now we've got this other sp2 hybrid orbital with an electron, and we haven't done anything yet. And that's what's going to form the bond with the oxygen. Okay, now to make that make sense, let me just separately draw what the oxygen looks like. We already showed that the oxygen is SN3, so that means it also has sp2 hybridization around it. Now let's describe it the same way, all right? If you know that it's SN3, SN3 will always have sp2 hybridization. In fact, the SN number, here's a little hint, the SN number will always match the number of hybrid orbitals you have. SN4, we had 4 sp3 hybrid orbitals. With SN3, we have 3 sp2 hybrid orbitals. Yeah, it can get confusing. That's why I tried to say that real slow. All right, so around that oxygen, we're going to have, just like we drew with the carbon, we're going to have the 3 sp2 hybrid orbitals in a trigonal planar configuration. And let's draw that plane again. Now, what's in, oh, I should draw the unhybridized p orbital too. We've got this, it's exactly the same, except one has oxygen as the central atom and the other one has carbon as the central atom. Now let's put the electrons in. Now I didn't show you what oxygen looks like in the ground state, but you should know what oxygen looks like in the ground state. But let's go ahead and draw it. So oxygen in the ground state, that's going to be 1s2, 2s2, 2p4. And we only care about the valence electrons, right? So we're going to have 2s2, and then for 2p4, it will be this. Okay? And this is now going to reorganize all these valence electrons, right? There's 6 valence electrons with oxygen. That you should know by now. Make that a little cleaner. They're going to reorganize themselves. We've got 2 lone pairs already, but they're going to be redistributed in these hybrid orbitals. And the lone pairs are going to be held in these hybrid orbitals. And then we've got the 2 unpaired electrons. One will be here in the other sp2 hybrid orbital, and the last one will be here in the unhybridized p orbital. Okay, now we've got the setup. We've described very carefully what these hybrid orbitals look like in the unhybridized p orbital and put where all the electrons are. And I already made the bonds with hydrogen, so you know what those sigma bonds look like. You could also make a sigma bond by overlapping hybrid orbitals. That's what we're going to get here. Now, I know you can't do this on your paper, but I can do it using my iPad. Right? If I bring these 2 together, sorry, I know you're groaning now, you can't do this. But you've got the videos, some people can. Bringing them together, now we have another area of shared overlap between those 2 sp2 hybrid orbitals. This is also a sigma bond. Right? Any sigma bond, you can form it a number of different ways. Here's an example of a sigma bond form between the overlap of 2 sp2 hybrid orbitals. With all of these sigma bonds, the shared electron density is along the bond axis, as shown. Here is my model of the carbon. And the white lobes are the 3 sp2 hybrid orbitals in a trigonal planar organization. Okay, you see that? So there are 3, they're about equidistant from each other and they're in a plane. Now, the purple lobes, that's going to represent my unhybridized p orbital. It's one orbital, but it's bilobe. So you've got a lobe that is above the plane and you have a lobe that's below the plane. Okay? Everyone see that in their mind now? Now in the model, we bonded hydrogen with 2 of these hybrid orbitals. So, all right, so here's the same model, except now 2 of those sp2 hybrid orbitals have formed a sigma bond with hydrogens. All right, and here is the sigma bond that's formed, and the axis of shared electron density, the area of shared electron density is along the bond axis, and we have 2 of them. The third sp2 hybrid orbital that has one electron in it, I'm holding it with my fingers. And we also have this unhybridized p orbital that also has 1 electron in it. Okay? So that's the carbon. Here's the oxygen. Same configuration. In white are the 3 sp2 hybrid orbitals. And now I've drawn in the lone pairs that are contained, that occupy 2 of those 3 hybrid orbitals. And then perpendicular to that plane, again, we have the unhybridized p orbital. It's 2 lobes. It's 1 orbital, but it's 2 lobes. Twisting the unhybridized p orbital. Let's put that here. And here's the unhybridized p orbital of the oxygen. And they're going to come together and they're going to form a sigma bond right here. Okay? Now I'm going to represent that sigma bond formed. Here's the carbon with one of the hydrogens bonded to it. I unplugged the other one because I needed the bond to form the sigma bond here. But there was another hydrogen bond right out here. Okay? You just have to imagine that it was there. Here, I'll be a magician. It's there, you just can't see it because my fingers are covering it right now. Okay? So you've got one hydrogen here forming a sigma bond, another hydrogen here forming a sigma bond, but you can't see it because my fingers are covering it. And then we have another sigma bond here in the middle that's hooking up the carbon with the oxygen. And then on the oxygen side, we've got 1 lone pair, 2 lone pairs in the other hybrid orbitals. And then, now when I say that there's free rotation around that sigma bond, right, here's a sigma bond. That's the area of shared density. I can rotate this in my model, and that mimics this idea of free rotation around a sigma bond. Now, the pi bonds that you get, just like we have sigma bonds that are formed from the overlap, pi bonds are also formed from an overlap, but in this case, they're formed from the overlap of the unhybridized p orbitals. So when these things line up, you will get overlap of the p orbitals. But the overlap looks kind of funny because the p orbitals are bilobed. So when they're lined up like this, we're going to get sharing of this density above and below this plane. It's just 1 bond, but the overlap, because it's bilobed, is above the plane and below the plane. The sigma bond overlap is along the bond axis, but the p orbital overlap, what forms the pi bond, is above and below the axis. So once you have that overlap, that stability of the overlap, you can no longer rotate this around. Okay? And it's kind of locked into place in its geometry. So here, the way I've drawn this picture, I already have the unhybridized p orbitals in red. They're already lined up. So to show that overlap when they're lined up is simply showing that when they're lined up, they will share their density. And the overlap is drawn like this. It's above and below the plane. It's deceiving because it looks like there's 2 bonds there, but there's not. You just have to remember that the p orbital distribution is bilobed. So the overlap of 2 p orbitals to form a pi bond is going to also be bilobed in this sense. One above the plane and one below the plane. So when you have this overlap, let's just keep it in red. The overlap of the unhybridized p orbitals, that's what we call a pi bond. And this is what we have in a double bond. Remember, we're still working on just formaldehyde here, using this new modeling theory to show how it represents the bonding in formaldehyde. It's a double bond. But with this theory, you can now look at what's really in the heart of this double bond. There's 2 different kinds of shared electron density in a double bond. One of the shared electron densities is a sigma bond, and it's along the bond axis. The second shared overlap of electron density is in a pi bond that you find above and below the bond axis, and it then restricts rotation around the bond axis. Okay? And that's how it's modeled in here. So this also restricts rotation. Actually, before I write, well, you already started writing it, so let's continue. Restricts rotation around the bond axis. And that's because the overlap is above and below the plane Well, actually, not even the plane. It's the bond axis. It's above and below the bond axis. That's the better way to say it. Whereas the sigma bond is along the bond axis, the pi bond is above and below the bond axis. So there's lots of different ways to make a sigma bond, but there's only one way to make a pi bond. The only way to make a pi bond is by showing an overlap between two unhybridized p orbitals, which means that if you have sp3 hybridization, you can't have a pi bond. You can only have a pi bond if you have sp2 hybridization or sp hybridization, because that gives you the unhybridized p orbitals to make pi bonds with. And in a double bond, then, a double bond is really composed of one sigma bond and one pi bond. Okay, so let's highlight a few things here. The pi bond is above and below the bond axis, and it also then restricts rotation about the bond axis because of that. And if you didn't like my picture of this, now you've seen the picture, though, created in front of your eyes with my very careful explanation. You can always go back to the textbook and find everything that I just did. It's all written for you in the textbook, and here's the textbook's version of what I just drew out for you. So you can always refer to this slide and go back to how it's described in the textbook as well. And we'll just use this picture, though, to highlight a few things, like the sigma bond here. Now here they're using the Greek letters. But to emphasize that this pi bond that's shown here, this is one pi bond. And I emphasize that because, look, it looks like two. And this always throws students for a loop when they see this. Here's another sigma bond. All right, the sigma bond is along the axis. The pi bonds are above and below the axis. Okay, so let's establish a few rules just to help solidify this for you. Like, these aren't really so much rules, they're just describing everything that I've just said. And you can just read this for yourself on the slide, but we've got time. I'll go over it just for emphasis. But I've already been telling you this. There are lots of ways to make sigma bonds. They can form between two s orbitals like we did with H2. Or they can form between one sigma orbital and a hybrid orbital. We saw that with methane, we saw it with ammonia, we saw it with water, we saw it with lots of things. We saw it with formaldehyde as well, that's CH2O. It doesn't have to always be an sp3 hybrid. This can be with an sp3 hybrid, that's what I showed you with these guys. It can be with an sp2 hybrid, that's what I showed you with formaldehyde. It could also be with an sp, which I haven't shown you yet. You could even have them between any two hybrid orbitals, and I showed you that also with formaldehyde, where the overlap of the sp2 hybrids, one from carbon and one from oxygen. So there's lots of ways to make that, but there's only one way to make a pi bond, and that's where you have non-hybridized p orbitals. It's the overlap. And so that's what you're going to have when you have double bonds and triple bonds. I just showed you an example of a double bond. And in that example of the double bond, we had one sigma bond at the core along the axis, and the second shared density was in the pi bond above and below. When you have a triple bond, as you'll see when we go over that one, we'll probably do that one. Yeah, we'll do that one next. It will have one sigma bond at the core again, but now there'll be two pi bonds. Okay? So let's actually look at a triple bond. Let's get a little bit more crazy with the artistry here. Now in a triple bond, the example here is going to be when we have a steric number of 2 about the central atom. And when you have a steric number of 2, as you can sort of see the theme evolving here, we're going to have 2 hybrid orbitals of equal energy. And those hybrid orbitals will be sp. There's 2. There's one s and there's one p. That leaves the other two P's unhybridized. Plus 2 unhybridized p orbitals. And for our example here, we're going to use the molecule acetylene, C2H2. This is acetylene is the common name, and ethine is the more formal nomenclature name that you'll learn when you go on and take organic chemistry. All right, well, what does this thing look like? So let's use this opportunity to do a little bit of review. So let's go and build a Lewis structure. We know how to do this. Carbons have 4 valence electrons, and there's 2 carbons. So that's going to give me 2 times 4, that's 8, plus 2 electrons coming from each of the hydrogens. So that's going to give me 10 valence electrons. Now we need to organize our skeleton structure. And I told you earlier that, well, when you have 3 or more, you don't put them in a line. You have one that's central with the other ones radiating out from it. But in this case, I'm going to break that rule. We have 2 carbons. And I did mention that when you have 2 or more carbons in a molecule, they tend to be grouped together in the center. So I'm not really breaking a rule, but I'm showing you something new. So we're going to have both carbons in the center here. And now where do the hydrogens go? Well, they have to go on the outside anyway, because hydrogen can only form 1 bond, because it can only have up to 2 electrons in its valence shell. So that's going to be our skeleton structure. That only places 6 of the 10 electrons. So the other ones, we start on the outside and we work our way in. But what's on the outside? It's hydrogen. So we need to only just put them on the carbons now. That's the only thing that's left. So 2, 4, 6, and then 8, 10. You know, I did tell you to fill up one before you move to the other one. And that just makes it easier. In this case, you'd still get the same answer if you split them up, but it's best to just stick to the rules. So as I've drawn this now, I have all 10 electrons placed. The one carbon with the lone pairs looks satisfied, but the other carbon is not. So we know how to satisfy it. We bring in lone pairs from the one that's full into shared pairs, and we need to do that twice to satisfy the carbon on the left. That will give us the final structure with a triple bond. And there you go. That's the final Lewis structure for acetylene. There's no lone pairs. They're all in shared pairs. You count them up, you still have 2, 4, 6, 8, 10 valence electrons shown in total. Now, what's the steric number around those carbons? It's 2. And I already showed you with the steric number of 2, you will expect to find 2 hybrid orbitals that are sp hybrid orbitals. And then they'll have 2 unhybridized p orbitals. If we look at those carbons, once again, in the ground state, when carbon is unhybridized, we know what that looks like. We don't need to keep looking at it. But when it now undergoes bonding to form a molecule where carbon is SN2, where it has sp hybridization, you've got the 2 equal hybrid orbitals, and you're left over with 2 unhybridized atomic orbitals. These are just good old variety p orbitals. Each one is bilo, but now we've got 2. So remember, back in quantum theory, those 3 p orbitals were in all 3 axes. So now these 2 p orbitals, they'll be found on 2 axes, as you'll see. So let's diagram what this looks like. And by the way, when you have 2 things, remember for Vesper, when you've got 2 things around a central atom, how would they be organized? Vesper, I'm sorry, say again? Linear. They'd be linear, right? With Vesper theory, if there's just 2 packets of negative charge and nothing else going on, now in this case, yeah, we have the p orbitals there, but just looking at the hybrids, the hybrid orbitals themselves will be organized in a linear configuration. So I think I was using bright green for these. So let's draw One carbon there, and let's draw the second one. I'm going to do the same thing to you. No, I won't do it to you. I'll draw them both here with the finished product. All right, so now I've just drawn both carbons, each with their sp hybrids. They each have 2. They're going to be linear. So they're going to be completely opposite to each other, 180 degrees opposite to each other around each carbon. And when you look at the finished product, all right, each one of these is going to have one unpaired electron in it because carbon's going to coordinate up to 4 things. So it's going to have, each one's going to have an unpaired electron. 2 of them are here in the hybrid orbitals, and 2 of them are here in the unhybridized p orbitals. Well, let's draw in the ones in the hybrid orbitals. Here's 1, 2 for the one on the right, and then I'll just use blue for the ones on the left here. 1, 2. And right here in the middle, we know what that is. That's a sigma bond. It's along the bond axis, and it is between, it's formed between 2 sp hybrids, hybrid orbitals. Now we also have hydrogens bonded here, and we know what hydrogen bonding looks like in these molecules. So let's put that in green. So we've got one hydrogen out here that's sharing its electron, and we have one hydrogen here that's sharing its electron. Now, of course, those are both in s orbitals. So here we have a sigma bond. And that one's formed between an s orbital and an sp hybrid orbital. But as you already know, there's lots of ways that you can make sigma bonds. Okay, so that explains all the hybrid orbitals and the bonds that it makes with the hydrogen. Now, what are we going to do with these 2 unhybridized p orbitals? So I'm going to draw them with different colors. So one I'll put in blue, and I'll try to draw it so that it shows that it's actually perpendicular to the bond axes here. And I'll put that one in blue, and then I'll put the other one. So if you imagine the bond axis is 1 dimension, and then the one that I just showed in blue is a 2nd dimension, and the 3rd dimension would be coming in and out of the plane of the screen. Okay, so I'll put that in red. I'll put going back and going out like this. Those are my unhybridized p orbitals. One color-coded in blue and one color-coded in red. Now, there's free rotation. I don't have a model for this one. Okay, I'll just remind you. There's free rotation, but now you know what a pi bond is. A pi bond is when you have overlap of these unhybridized p orbitals. You can only get that when they're aligned. So you might imagine that you can get rotation around this axis here until these unhybridized p orbitals are aligned. Now, I just arbitrarily drew one in blue and one in red. Okay, but I could have swapped them up. It doesn't matter. The point is that once they're aligned, you're going to have overlap of the blues in this case, and that's going to form 1 pi bond. And then you're also going to then automatically get the other pi bond form because these are all orthogonal to each other. So once one is lined up, whoops, the other one's going to be lined up as well. And you'll get overlap of the reds. Now, they're both above and below the bond axis, but in this drawing, the blue one is actually above and below the bond axis. The red one is behind the screen and in front of the screen, but it's still above and below the bond axis. The point is this, that it's not along the bond axis. Each one would lock it into place. It wouldn't rotate once you have a pi bond form. And so let me just emphasize, there is 1 pi bond here in red, And there's a second pi bond here in blue. Right? And this is giving us our triple bond. And in the triple bond, we've got 3 shared pairs of electrons, right? 3 shared electron pairs. And of those 3, one of them is along the bond axis. That's our sigma bond. And 2 of them are above and below. That's our pi bonds. And there's 2 of them. Oops. And once again, here's the textbook's description of that. You know, it's one thing to just look at an illustration in the textbook. It's another to actually see the illustration being made while it's being described. So now you've got both to use to try to understand. And yes, this is a very conceptual model. It's very difficult to draw. That's why I like spending a lot of time on this, because I think it's an important concept to try to understand. This model actually works really, really well at explaining a whole bunch of things that the individual models didn't do a good job of. And I'll mention some of those in a little bit as I get more to summarizing this. All right, so let's just go on to this slide here. All right. So I already mentioned to you one of the trends that we found in going through these, that the steric number, and we know what the steric number is, but I'll just go ahead and remind you. That's the number of bonded atoms plus the lone pairs. I mean, I've been describing it as packets of electron pairs, but those packets could be in shared pairs or they could be in lone pairs. And a single bond, a double bond, a triple bond, that's still one packet of shared electrons. Now, as you've learned, the steric number is also going to be the number of hybrid orbitals. As we've been describing. So just to summarize, when you have an SN of 2, that means we're going to have 2 hybrid orbitals. And we know what those are called. Those are the sp hybrid orbitals. And that means we've got 2 unhybridized p orbitals left over. And the example that I showed you for SN of 2 was acetylene. So let's just put what the example was here. And from that, you can get a triple bond. You don't always have to have a triple bond. For example, carbon dioxide is also SN2. Okay, but it's not a triple bond. You've got 2 double bonds instead. And if we spent the time, or you can just go and see this one in the textbook for yourself. It's still sp hybridized around that carbon because the steric number around that carbon is 2. All right, that means that you've got 2 unhybridized p orbitals around that carbon, and you've got 2 sp hybrid orbitals. Each of those sp hybrid orbitals is involved in the sigma bond that's at the heart of those double bonds. And then you've got the unhybridized p orbitals that make the rest of the double bond, but now you have 1 on each side. Okay. You've got SN of 3. There we have 3 hybrid orbitals, and those are sp2 hybrids, which means you have 1 unhybridized p orbital. And the example I showed you there was formaldehyde. And then, of course, last week we started with SN4. That's where you're going to have 4 hybrid orbitals. And those are sp3 hybrid orbitals, which means you have no unhybridized p orbitals. And we looked at a number of molecular geometries that you get with SN4. If you have all 4 atoms bonded to it, you would have, for example, methane, and I'll try to draw that in 3-dimensional. That's going to be a tetrahedral geometry, molecular geometry. But I also showed you examples where you have only 3 bonded atoms, like in ammonia. And that's going to give you your trigonal pyramidal geometry. Or you can have only 2 bonded atoms, like with H2O, and that would give you the bent. Right? But all of those have an SN of 4 around that central atom, which means that the hybridization is going to be sp3 hybridization, and there's 4 of them. It's just a matter of whether they're all involved in covalent bonds or if some of them are housing lone pairs. This is just review because I showed you examples of all of these. But now let's take it a step further, because one of the other things that this theory shows very, very well is this idea of hypervalency. So you remember the expanded octet and hypervalency, where you can have more than 8 valence electrons, or what appears to be more than 8 valence electrons around the central atom. And I explained to you at the time when we did this with Lewis structures that this is what we observe. These molecules display hypervalency, but what model do we have that explains how that can be? And I mentioned one thing to you. There are several models that explain hypervalency. This is just one. Now we can actually take a look at it. It involves the use of the d orbitals that you only have when you're at a principal energy level of 3 or higher. That's why oxygen, nitrogen, carbon, they can't have an expanded octet. But things in n equals 3 or higher, like sulfur and phosphorus and selenium and silicon, those can have expanded octets. Well, this model actually explains how you do it. It's again with this idea of hybrid orbitals. Just like I showed you before, but without going into the same level of detail, if you have an SN of 5 or an SN of 6, well, maybe you've made that realization by now. Those are all going to be molecules where the central atom exhibits hypervalency. And where does it get those orbitals from to make the hybrid orbitals? It's the same idea. For SN of 5, you're not only going to merge the 1s orbital with the 3p orbitals, but you're also going to merge 1d orbital in there. With an SN of 6, you're going to merge the s and the 3p orbitals with 2 of the d orbitals. And it's all shown for you here on the slide. I don't need to go through what that ends up looking like in the end, except just to circle it, all right? You end up with 5 equal energy hybrid orbitals. And here you have 6. All right, and you, by now using Vesper theory, you know what the base geometries will be. Right, this is going to be trigonal bipyramidal. And you know that if you have 5 atoms bonded to each of those hybrid orbitals, you'll have a trigonal bipyramidal molecular geometry. And if you have only 4 of the 5 bonded to atoms, you're going to have this seesaw shape. Or if you have only 3 of the 5 bonded, you'll have a T shape. Or if you have only 2 of the 5 bonded to atoms, you can actually form a linear shape. This is all stuff that we talked about earlier with Vesper theory at the different steric numbers, but now you're seeing it again from a different angle. Same is true for the SN of 6. You know that this base geometry is octahedral. That's what you get when you have 6 equal energy orbitals that are all distributed as far away from each other as possible, but given that they all have to stay attached to the central atom. And where we get those 6 from is from these atomic orbitals that hybridize with this bonding theory. And we looked at the different shapes that you would get if you only had 5 of those 6 orbitals bonded to atoms. If it's 5, that would be the square pyramid shape. And if you have only 4 of the 6 bonded to atoms, that would give you the square planar shape. And that's pretty much where we left it off. Okay, so this model actually explains hypervalency. Very well, but it's using d orbitals. As I said, when you go on to organic chemistry, you'll learn about molecular orbitals, which has its own way of explaining hypervalency. Again, hypervalency is something that exists. This is just one model that can explain it and predict how it actually occurs. Why should you care about valence bond theory? Well, to start with, at the very beginning, it merges what we learned from quantum theory and puts that into context with what we observe in nature with equal energy bonds. Number 2, it explains hypervalency really well using d orbitals. But let's use this model to understand what I mean by stabilization with the resonance forms. And for my example here, we'll use the carbonate ion. This is one of the polyatomic ions. It's the carbonate ion, right? CO3 2-, and it's a polyatomic. Here's the Lewis structure. Now, I'm not going to take you through that. I'm sure this is one of many that we did way back in chapter 4. And in the end, we needed to show that to make the final Lewis structure, there were 3 possible oxygens that we could have taken the lone pair from. And so I made you draw all 3 of them, because in the Lewis structure model of covalent bonding, that's how we can describe resonance stabilization, by showing that you can have all 3 available. And then we talked about the bond order and how we would calculate that from the Lewis structure. Okay, all the bond order is doing is giving you a feel for the fact that if you looked at one of these molecules, you wouldn't find 1 double bond and 2 single bonds. Instead, you would find all 3 bonds have the exact same length and the exact same bond strength, and it would actually be a hybrid of these 3, a hybrid of the 2 single bonds and the 1 double bond. But what does that mean, a hybrid? What does that even look like? Valence bond theory allows us to take a look at that. All right, so let's now build these. But let me write a few things here. So all three bonds are equal. Right? Equal length and equal strength. And we even described the bond order. The bond order, we had four bonds, or four bonded pairs. Let's write that, 4 bonded pairs divided by 3 atom pairs, or just 3 bonds. 1 double bond and, 2 double bond, 1 double bond and 2 single bonds. And that gave us a bond order of 1.33. Again, this feel for all 3 of them would be about 1/3 double bond character and 2/3 single bond characters. And you can kind of get that from the resonance forms. So what does this look like in the valence bond theory model? Because overall, it's greater stability. So resonance forms, this equals greater stability in the molecule. So if you can undergo a chemical reaction that allows you to redistribute your electrons so that they can be in resonance like this, that will be a more stable state for it, and that will be the driving force for the reaction. All right, so let's now use our artistic skills to show what the carbonate ion looks like. So first of all, let's look at the Lewis structure. What's the steric number on that carbon? It's 3. Remember, this is 1, 2, and 3. Okay? Now, it may not look like it on these oxygens because the way it's drawn in the Lewis structure, but if you figure that all 3 of them are equal, all right, then the steric number on the oxygens will also be 3 because you're going to have 1, 2, and 3 because they're all going to be basically partially sharing one of those lone pairs on each of them. Again, it's hard to conceptualize in the Lewis structure. All right, well, let's first draw the carbon. So with SN3, we know that it's going to be, here, it's written right here. With SN3, the carbon is going to be sp2 hybridized. So that's going to be, in green here, that's going to be 1, 2, 3. Those are my 3. Here, let's draw these a little bit more equal. These are my 3, whoops. These are my 3 sp2 hybrids. Okay? And now let's draw the oxygens. They're also going to be sp2 hybridized. So let's just draw one of them over here. That's 1, 2, 3. And actually, let's just draw them all in. There's going to be one here, and there's going to be one here. And each of those oxygens is going to be sp2 hybridized. Now let's put our electrons in as well. Now here we have a sigma bond between the carbon and each of the oxygens. We have a shared pair there. And in the oxygens, notice that the oxygens here, 2 of those hybrid orbitals are going to have lone pairs in them. So let's put the lone pairs in. They're not going anywhere. All right, so we're almost done. That shows the sp3 hybrid orbitals. Now they each have 1 non-hybridized p orbital. So we got to draw that in. And just as I did before, I'm going to draw the lobes of the unhybridized p orbital like this. And I'm drawing them already aligned because remember, there's free rotation around each of those sigma bonds, but you'll get the pi bond formed when the orientation is such that the lobes of the unhybridized p orbitals can overlap. So that's what I've drawn here. Now consider if we just looked at one of these carbon oxygens, then you'd say, okay, well, I know what to do with this. They're overlapping, so I have overlap here, and I have overlap here, and that's a pi bond. So in oxygen, if you remember from before, there's 1 unpaired electron in each of these unhybridized p orbitals. And there's 1 unpaired electron in the unhybridized p orbital from the carbon as well. All right, we can make a pi bond here from sharing those 2 unpaired electrons with the overlap of the p orbital, but now that 1 unpaired electron in the carbon, it's used up. So how can we share it with anything else? That's where this idea of resonance comes in. You don't just have 1 pi bond like this. In fact, you don't have 3 separate pi bonds. Instead, you've got 1 giant delocalized pi bond across the whole thing. All 4 of these electrons, 1, 2, 3, 4, these unpaired electrons, they're all being shared in 1 distribution that's above this plane, okay, and in a distribution that's below the plane. just like I showed you for an individual pi bond, but now it's delocalized across 3 different pi bonds, or in this case, 4 individual unhybridized p orbitals. So what we have is delocalized pi bonds. We're basically sharing all 4 unpaired electrons across one delocalized pi bond. It's basically across all of the unhybridized p orbitals. It's delocalized. Why is that more stable? Because it's a negative charge. You've got 4 electrons. And are you going to confine electrons just to one area of shared space, like we have in a sigma bond? Or even between the 2 lobes of one pi bond? This is even better. The further you can distribute electrons from each other, that's what we learned in the Lewis structures. How do we best distribute those electrons so that they can be as far away from each other as possible, yet still be a part of these bonds? That's what we learned from the Lewis structure. The same idea is here with resonance. With resonance, we can delocalize those electrons over a much wider area. Distributed over a much wider area, yet it's still part of the molecule. Right? And that, my friends, gives you overall greater stability. And I think I already mentioned several times in this class that the driving force for anything that we're describing, why do ions form? Why do bonds form? It's all driven by stability. So even though it's really difficult to draw, okay, the whole idea behind valence bond theory and sigma bonds and pi bonds does a really good job of explaining conceptually why resonance forms give you greater stability. Because this shows you, in orange here, the greater distribution of those electrons. You don't see that up here with these Lewis structures and resonance forms. So again, it's just what does the model show you and how does it help you conceptualize what's going on? If you want to see an even greater example of this in the textbook, carbonate ions not in the textbook, but this one is benzene. I won't go through benzene, but it's the same idea. If we were to go through the time and draw out all of the hybrid orbitals here and overlaps for benzene, you'll see again that you get this overlap of, it's shown up here, one overlap above the plane and one overlap below the plane. Again, it's the same idea. It's the delocalization of those unpaired electrons in one massive pi bond. It gives you much greater stabilization. All right, so that was a bit of a mind bender, but